Okay, sorry about that. All right, off we go. So the second of two lectures exclusively about divide and conquer, which we started last week. Yesterday. Tuesday. Again, out of these two kind of themes, this probably is most closely aligned with identifying subproblems. But the point of emphasis has changed from dynamic programming, as we discussed last time. So when we're doing divide and conquer, where we take, for example, merge sort, usually the problem at hand is kind of obviously in polynomial time. It's not surprising that we can sort. But the emphasis is trying to do this basic thing even faster. So it's about dividing the subproblems to really minimize overlap in any work. Whereas for the kind of dynamic programming type of problems, it's often less obvious that there is a polynomial time algorithm. And the subproblems are kind of set up to be more, exhaustive, trying a lot of combinations, making sure you don't miss anything. Okay, but still trying to make sure that at least the number of subproblems is a polynomial and not exponential. Okay. And compared to divide and conquer, there tended to be a lot of overlap between problems, and as part of sort of our exhaustive approach, we tend to have lots of dependencies where we're exploring many options. And the only reason that sort of this try everything approach doesn't generally explode is because we do save our answers and avoid some redundancy. Okay. So, last time we did two problems. One was integer multiplication. The other was selection, selecting an element in linear time. I'll just remind you. So integer multiplication, we're trying to multiply two n-bit integers. And the old-fashioned way was like a table, or kind of this array, that we used to do. It used to take like n squared time. Okay? But there's this famous trick due to Karatsuba from 1960 that shows that, normally you can try something where you kind of divide each of your two integers in half, bitwise. So kind of the n over 2 least significant bits, n over 2 most significant bits. And there's a natural way to turn it into 4 recursive calls, which would just get you back to an n squared time. But with a little bit of cleverness, you can actually reduce it to 3 multiplications by just noticing some redundancy with some basic algebra. Okay? And having 3 recursive calls instead of 4 gets us from n squared to n to the log base 2 of 3, which is like 1.58 or something like that. Better than n squared. Which is just kind of surprising because integer multiplication is something we took for granted. Okay. The second problem, also kind of a very simple problem, was selection. It's closely related to sorting. I'm giving you an array of comparable elements, and I say, give me the 100th smallest element. And of course, you can sort your whole array first, and then just go to spot number 100. The only question was whether you can do it faster. Okay. And so we explored some divide and conquer strategies based on the idea of a pivot. So like an ideal case, suppose that maybe you want some arbitrary rank, but suppose you could get the median. That will let you kind of split the input in half each time, get the median element, and figure out if the rank you're looking for is less than or bigger than the median, and recurse on the appropriate half. And you never actually have to sort the elements, you just kind of keep dividing in half, and that gets you in linear time. Of course, we don't actually know how to get the median in linear time, but approximate medians suffice, as long as it's somewhat close to the middle and not too close to the edge. You'll still get that geometric decreasing sequence when you do the recursion tree. Okay. And then finally, to supply an approximate median, we use this very clever median of medians trick, where roughly we kind of took our input and divided it into groups of 5. Each group of 5 is very easy to find the median. and then you have only n over 5 elements left, so you've decreased the input a lot, enough that you can actually afford to recurse and get the exact median of this subsample. And the median of medians will still be like within the middle 40% or something. It'll get rid of at least 30% of your elements on both sides. It turns out we can still set up a recursion tree and still get a geometric decreasing sequence with this much weaker median. And you get a linear time selection. And in particular, you're selecting things without ever sorting the whole array. That's pretty cool. So actually, we even showed that you have to use n log n to sort the whole array. We gave a lower bound. And here we're actually able to kind of... The lower bound doesn't apply to selection because you're not sorting the whole thing. Okay. All right, so our next two examples for this class, probably a little bit more mathematical in calculation, but hopefully the focus on the algorithmic part where we're actually getting some speed up in running time. So one has to do with finding the minimum distance among a bunch of points in a plane. The other is this fancy thing called Fourier transforms. I'll explain that when we get there. That's probably the most. That probably will have the most definitions, mathematical definitions, which is a little annoying, but it is actually probably the most useful thing that I'll present this week in real life. Okay. All right, so let's look at the distance problem. So your input consists of points in the plane. So just xy coordinates. You have n points, each corresponding of 2 real values. And the goal is to figure out the minimum distance over all pairs of points in the plane. So just to remind ourselves, the Euclidean distance is sort of this Pythagorean-looking thing. Rats. Right, so given, I did it wrong. Given x and y, the distance will be kind of the difference between each coordinate squared added up and taking the square root. So you'll get x1 minus y1 squared plus x2 minus y2 squared, and you take the square root of that. Okay, so that's how we deal with diagonals. Okay, so you just have a point set. You want to go through, find the minimum distance. The easiest thing, of course, is to go through all pairs and figure out the minimum distance. And that would take roughly n squared time, where for each we do this sum of squares and the square root. I'm not sure what the minimum distance. In this one, maybe it's these two. That might be the closest pair of points, which have some distance, which is like delta, which for me is, 2 feet on the projector. Okay. And the goal is just to identify this. Okay. Yeah.
I'm pretty sure your initial formula was correct. x1 minus x2 squared, the difference in the two x's, and then the difference in the two y's, right?
Oh, okay. Okay. I guess it depends on the notation. Okay. So let's say that x, I think actually I might be inconsistent, but in that formula, let's say x is specified as x is equal to x1, x2, and y is equal to y1, y2. So, okay, I shouldn't have used x and y. So, x1 is the x coordinate of x. x2 is the y coordinate of x. y1 is the y coordinate of y. y1 is the x coordinate of y. And y2 is the y coordinate of y. Okay. My dad's an engineer. The one advice he gave me was, don't use i's and j's for your loops, because they're the only two letters that look the exact same. And of course, that's all I do. And I guess this is the mathematical analog. Don't use x and y for your points because you need x coordinates and y coordinates. And of course, that's the only thing that came to mind. Okay. All right. Yeah.
So the goal is to only find one point, or all?
The goal is to find the minimum distance over all pairs of points.
So just one distance?
Yeah, so ultimately you output one value. And we're not worried about whether multiplication takes a long time or anything like that. We're just assuming we can do math. Okay. Right, so we want to do better than comparing all pairs. Right? And even just looking at a picture like this, it's in 2 dimensions, so this is a representative picture of such a problem. And just, when you just look at it from this bird's eye point of view, you kind of know that, like, oh, comparing these two is ridiculous. Right? And comparing these two is ridiculous. Right? It's a little bit hard to figure out how to express this to a computer, but you already know in your head there's some geometry. Opposite ends of the map, so to speak, are unlikely to be the closest point. Right? So it does seem like checking all pairs is redundant. Some pairs are obviously not going to be the closest pair. And but somehow, how do we kind of put our finger on that intuition and do some divide and conquer? Okay. All right, so let me give as a warm-up, let's pretend all the y coordinates are 0. So this is like the one-dimensional case. Right? I give you a set of points. All the y coordinates are 0. It's really just a one-dimensional problem. What are some ideas for the one-dimensional case? Yeah?
Only compare adjacent points.
Okay, only compare adjacent points. Now, only to do that, though, it is true that I drew the points on the line, but in general, I just give you the points. So you have to do one pre-processing step. I got to sort the points. Yeah. Sort the points, and then we can just scan and compare all these consecutive pairs. Okay, and it looks like maybe this consecutive pair would have been the closest. Okay. Our running time would have depended on sorting, so we're taking n log n time. Yeah?
Wait, you're sorting the distances?
No, I'm sorting the points. So this picture is just a little bit misleading because, yes, I gave you points on the line, but when I give you to you as a computer, I'm just giving you a bunch of numbers. You still have to sort the points to kind of effectively place it on the line. Yeah. Then you only have to scan through and check the consecutive pairs and keep track of the minimum. You don't really have to. You could make a list of all this and sort it, but for minimum, we just keep track of the best one we see. Okay. All right. So that's the most natural idea, but it's hard to generalize this to 2 dimensions because it's not clear how to sort 2-dimensional points. I can sort by x, but it doesn't tell me much about y. Okay. Let's see if there's a different way for 1 dimensions to get n log n without explicitly sorting the points, but more kind of divide and conquer. I guess sorting is implicitly divide and conquer if you use merge sort, but let's put that aside and think about this. Not sure if this question will be clear enough to be answerable, but let me still try. Is there a second idea that anyone can think of, which is clearly dividing stuff up, that would also lead to a similar running time? Okay, if I told you I was going to try to divide the point set in half, what's a natural way to try to divide the point set in this one-dimensional case? Yeah. Okay, the median. Okay, good. So one idea is use our median algorithm from last time. Find the median x-coordinate. Okay. And maybe for simplicity, let's say it's actually here. And recurse on both sides, right? And kind of find the minimum distance on this side. The minimum distance on the other side, right? And then maybe I would look for the leftmost point on the right and the rightmost point on the left, and I would compare it to the sort of those first points on either side. And so, the minimum pair is either on one side or the other, or it's going to go across the middle. And if it's going across the middle, I should only check the nearest points to the middle. Okay? So, this would also give us, it only takes linear time to find the median now. We'll get this kind of running time, which is the most common one we've ever seen. So this is the same as merge sort. Okay. We'll get n log n. Okay, so that's an alternative approach. There's something implicitly, it's a little different than, I guess, sorting and scanning. Because merge sort doesn't divide in half that way. The sort divides in half arbitrarily. Okay. So this approach we'll find is going to generalize a little bit better. Okay, so we're going to try to take this approach and generalize it to the plane. Okay, so what do we have written down? Okay. All right, so let me explain. Maybe I'll draw some of these. Okay, so here is one idea to try to generalize. It might seem a little asymmetric, but nonetheless. Okay. So I have points in the plane now. And step one is I'm going to get the median x-coordinate. And just imagine a line there, splitting the point set in half. Okay, so think of that blue line as the median. Okay. And then we'll recurse on both sides and find the minimum distance on left and right. So on the left, maybe this is the closest pair. On the right, maybe that's the closest pair. That seems to be a little bit less. Okay? But I divided in half, and I'm recursed on both sides. And all that remains now is to check the pairs that are going across the middle. One on each side. Okay? Now, in doing so, at some level, I know that there's no reason to go any further. It looks like delta 2 is smaller than delta 1. So let me call this delta. There's no reason to go any further than delta to one side if I'm looking for distances smaller than delta. And I'm going across the middle. Okay, so I can kind of imagine a vertical line like that. Okay. And likewise here, there's no reason to go further than delta if I'm just trying to get the minimum distance across the middle. Okay, any point that's further to get across has to at least already go distance delta, where delta is the minimum found on either side. Okay. Okay, so at some level this is sort of the merging step if we thought of it like merge sort. But I'm just going to look at that middle band. I know I only have to look in the middle to find the closest pair across the middle. And somehow we'll try to focus on that problem. Okay, so that's the higher level setup. Split it in half xy's. Get the minimum distance on each side. And then we use that minimum distance to sort of focus in on a relatively narrow band in the middle. Okay. All right, so we still have to figure out how to do that. Okay. All right, so let's look at this band. At some level, delta we should, yeah.
When you take that delta is the minimum of both sides, right?
Yeah.
The minimum for both sides.
It's a minimum out of the two answers we got from left and right, which I thought would have been that pair on the right. Yeah. Okay. So we should think of delta as being pretty narrow in that it's the minimum distance between any pair except the ones going across the middle. It's sort of a small number. So intuitively it's kind of narrow. And if I look at the points on the left side of the blue, the left side of the median, I'm only looking at those pairs. I know all those pairs have to be delta apart. Right? Because that was delta is less than or equal to any distance just on one side of blue. Okay. So if I'm looking at this narrow band, any of the points on the left side of the narrow band have to be at least distance delta apart from each other, any pair of points. Any pair of points on the right side has to be at least delta apart. Because again, delta is less than or equal to any distance, any pair just on one side or the other. Okay, so you have this very narrow column. Very sorry, and just once on one side, all the points have to be roughly the width of the column apart. So at some level, each side can't be that crowded. Right? All the points are spread out in proportion to the width. So it's not going to be that crammed on one side of this column or the other. Okay? So the intuition then is that there's something kind of simpler about this middle band. It can't be that dense. And so you're hoping that not that many comparisons are needed. Right? At some level, it's kind of obvious, or it might be easy to articulate that there's no reason to compare the top and bottom of this thing when it's... Yeah. At some level, I know that if I'm looking at a point here, right, and I need to compare this point in the middle to other points in the middle. And I sort of know that I only have to go delta up and delta down and check to see if there's other points in this box. Okay. Any point outside that box is going to be really far from that point that we're currently interested in. But the intuition is that box can only have a limited number of points because it's sort of spread out. Okay, so what we're kind of doing is that for each point, we're going to only focus on that delta width or 2 delta width square around it. Okay. And we're going to argue that that square is not very dense. It doesn't have to compare itself to that many points. In fact, we'll show that it only has to be compared to like 10 other points or something like that. Okay. Sorry, this microphone is very excited. All right, any questions about the intuition? Because we're going to now try to formalize this idea. Yeah?
How do you establish that box without checking the distance for every...
Oh, okay. So I haven't given... let's see, what's next? Okay. Yeah, okay. So I guess I haven't given the full algorithm. Let me explain the full algorithm then, which will answer how do we actually do this concretely. Okay. And then I'll go back and show that you can do some shortcuts. Some of the shortcuts the algorithm takes are valid. Okay, so, all right, so what do we do? Okay, so we've already discussed. Let's get the median x coordinate. Let's divide the point set in half, P1 and P2. Okay. Let's recurse. Get the 2 point sets. Well, let's get the minimum. That should be delta 1 and delta 2. It says delta 1 and delta. Okay. And now, I'm assembling a set P3 of points that lie in the middle band. Okay, here's another typo. That Z should be A. At some point I changed all the Z's to A. Okay. So, P3 represents all the points in the middle band. Okay? And sort those points by y coordinate, which takes n log n time. Actually, if you're clever, you should sort all the points by y coordinate before starting this whole algorithm, so that when you come to this stage, it's kind of already in order for you. Okay? So this might be P1, P2, P3, P4, P5, P6, something like that. So now the points are just sorted. I haven't done any pairwise math. Okay? Now if I was, for example, interested in P4, intuitively, this won't be what the algorithm does, but intuitively I know I should only have to kind of check the height delta. I should use maybe some different colors. Okay, not green. Okay. At some level, I'm only interested in this horizontal band, because outside that band, the distance is definitely bigger than delta. Okay. And what we're going to argue is that in this red square, there can only be like 10 other or 20 other points. Okay, so we'll prove that next. In this delta by, or 2 delta by 2 delta squared, there can only be like 20 points. Okay? So what the algorithm's going to do, actually, is, so that means I kind of know that P4, I should compare it to P5, P6, P7, up through P15, but I don't need to compare it to P16, or P17, or P18, because those points will definitely be outside the box. So it's sorted by y, and then I kind of know that I only have to check a few nearby y coordinates, because there's only so many that can fit in the box. Okay, so that's why here I'm only comparing pi and pj. J is bigger than I, but not too much bigger than I, say within 10. Okay. So now all that's left is just a geometric argument to try to say, hey, there can only be so many purple points in one of these boxes. And that's why I don't have to compare everyone. I only have to compare the closest 10 by y coordinate. All right. Does that make sense, the high-level intuition? Now all that's left is very localized. Okay. Okay, so here's the lemma. Okay, so I'm using A for the x-axis, and let's say that the y-coordinate that we're interested in is B. Okay, A comma B. And so, okay, what the lemma is saying is that if I'm at point AB, and again we have sort of a blue line going down the middle, okay, and I'm looking at this square, where I go delta in this direction, delta in that direction, delta in that direction, okay, and I want to know how many points are in that square. Okay, so actually, what I'm doing is that for this point, I'm only worried about the points that are below it. Okay, so the claim is that there's only at most 10. Yeah, it doesn't really matter what the number is. I think you could get it down to like 6 or 7. And you could be lazier than what we're doing and say 20 or 100, and you'll still get the main running time, which is to say that you only have to check a constant number of other points. Okay, so how do we prove this? So I'll only mention that the style of argument is very common in computational geometry. It's called a packing argument, because we're going to kind of argue that you can only pack in so many of these points because they have to be spread out from each other. Okay. All right, so dividing this down further, I'm going to say, let's call the left half L and the right half R. Okay? And I'm just going to focus on L. Okay. All right, so, okay, well, how do I look at this? Should I use this picture? Okay, let's use this picture. All right, so I'm looking at that left side of that rectangle underneath that I'm analyzing. The same argument will apply to the right side, no different. Okay. Now, okay, so this square has height delta and width delta. Okay. Now, every time there's a point in that square, I'm trying to count the number of points in that square, I know that it has to be delta apart from any other point in that square. Right? So imagine drawing a circle of radius delta over 2. Okay? Imagine drawing a circle of radius delta over 2 around each of the points in that square. Since everyone is delta apart, we know that these circles can't be overlapping. They might meet at the boundary, but the interior will be disjoint. Okay? Because the radius is half the distance. So, at some level, these circles are sort of carving out some area for themselves. Right? That circle owns that amount of area. No one else touches it. Okay? Now, all these circles are going to sit inside this square, which what I've done is I've added delta over 2 padding on all sides of that square. Right? Because the circle has radius delta over 2. So the circle will fit in that outer square, which adds the padding. Okay. So the height and width of this outer square, will be 2 delta. So every point carves out a circle with radius delta over 2, all for itself, and also sits inside this square of height and width 2 delta. Okay? So if I gave you those facts, how can I argue that there can only be a limited number of points? Why can't there be a million points under those, oh my God, circumstances? Why does this setup, these interior disjoint balls in the limited space, what's the punchline? How do I now argue that there can only be so many points? Might seem odd, yeah.
Because if there were any closer together, you would pick a different delta.
Yeah, okay, so yes. So intuitively it's 100% correct. I mean, it seems obvious, right, that there can't be that many. I can't pack that many circles in there. But all that's left is, how do I articulate this? Instead of just looking at it and be like, oh, it must be obvious. Yeah.
For circle has a given amount of area, and there's only a given amount of area.
Okay, so we can use the area to say, there's only so much area available, and each circle uses up a certain amount of area. So we set up some kind of constrained resource to limit things. So the area of the outer square is 4 delta squared, 2 delta times 2 delta. And down each ball has area pi r squared. So that's like delta over 2 squared. Okay, so that limits the number of such balls we can fit into the square. Okay. So that's 16 over pi, which is 5 point something. I checked. Pi is a little more than 3, so. And it has to be an integer, so we can round down. So we conclude there can only be at most 5 points with their center inside the smaller square, because that puts the whole ball in the outer square. Okay, so it's an area packing argument. If they're spread out, they take up space. There's only so much space. Okay. All right, so that shows there can only be at most 5 on the left side. There can also only be at most 5 on the right side by the same argument. I guess I could have done the whole rectangle instead of a square as well. All right, so the points have to be spread out in something, and that minimum distance is sort of proportional to the whole size of the square I'm interested in, and that's why the number of points becomes limited. To articulate it, we have to do this area division. Okay. All right, so that is why in the algorithm, I only have to check 10 points. Okay, instead of checking all pairs of points, there's only so many points that could fit in a square. 10 is an upper bound, so 10 is conservative. And so as a result, this last step, instead of comparing all pairs of points in the vertical band, I'm only checking like 10n. I'm only computing 10n distances or something. Okay. All right, so as far as the whole running time goes, I've already annotated the lines. Computing the median takes linear time. Dividing the point sets in half takes linear time. We have 2 recursive calls to half the point set. I assembled the vertical band, and then I do only a limited number of comparisons within the vertical band. Okay. Sorry. So here's the recursive running time, and we've seen this before. What is this? n log n. All right, sound good? Probably the only geometric algorithm we'll see in this class. Okay. I'll mention there's a lot of this. If you do computational geometry, I mean, the name of the game is splitting the point set along horizontal and vertical lines, and you can get very fast running times for all sorts of geometric problems because it tends to be very kind to divide and conquer. Okay. Okay. All right. On to the last one, the scariest one. These are Fourier transforms. Okay. The algorithm itself is actually not at all the most complicated. I think this vertical band and thinking XY is in some ways more complicated. I think medians is also more complicated. But Fourier transforms mathematically is all about complex numbers, which we usually don't work with every day. So let me try to give you a very fast primer. Okay. All right, so the complex plane is sort of like 2 dimensions. You have your real dimension, as usual, and then you have an imaginary dimension. Okay. So the numbers have the form not the eraser, okay. A plus bi Okay, so they're like two coordinates. I is the infamous imaginary I. I don't know why they call it that. I think it's a bad name. But it satisfies I squared equal to -1. Okay, that's the only rule we're concerned with. Okay. And that tells us how to multiply complex numbers together. If I'm multiplying a plus bi, that's one complex number, times another complex number, c plus di, so that's two coordinates each. Then we just do the usual algebra. Okay, so a times c, and then here's the cross terms, bc plus adi. And the only thing weird is we get minus bd, because originally we get bdi squared. The I squared becomes -1. Okay. So those are just the rules we're playing with. Okay, it turns out there's lots of good mathematical reasons for having a system like this. Okay, actually, math in the complex plane behaves much more nicely than math in the real plane. For example, a polynomial of degree n always has n zeros if you're allowing for complex numbers, but that's not true for real numbers. I mean, x squared equal to -1 doesn't have any real zeros, but I and -I are both zeros of x squared equal to -1. So there's a lot of nice stuff. But now that I've defined how to multiply two complex numbers, then I can start talking about polynomials of complex numbers, because polynomials are just multiplying a bunch of complex numbers. Right? So something like if I gave you the function p of x, which is equal to a0 plus a1x plus a2x squared up to a minus 1 x to the n minus 1. Right? Of course, you're used to this for real valued numbers, but you can also do it for complex valued numbers because you know how to multiply two numbers at a time. Okay, it just follows the same rules, and your intuition will largely hold, almost entirely hold. Okay. But now when I look at a function like e to the x, it's not clear what e to the x is when x is complex, except you can actually think of the exponential function as a polynomial, an infinitely long polynomial, so-called a convergent power series. But you may know that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial and so forth. So it's an infinite sum. But actually those 4 factorials, 5 factorials, 6 factorials grow so fast, this sum always converges. It won't go off to infinity. It's much faster than a geometrically decreasing sequence for any fixed x. Okay? So the fact that e to the x can be expressed as a polynomial with some technical care for the fact that it has infinitely many coefficients also means that now, e to the x when x is complex makes sense. Because I'm just evaluating this polynomial for complex numbers. Okay, so all these things are well defined. Okay. Mind you, there's whole classes on complex numbers, and I'm doing this in about 5 minutes, so I'm just giving facts here. Okay. One way to think of, the same way that complex numbers are two-dimensional, that means there is some reason to maybe think of it as polar coordinates sometimes. But this is captured in what's called Eulers formula. So again, we've already defined e to the x. Now, if I have some real value theta, okay, and I ask myself, what is e to the theta I? So theta I is a complex number. Okay. It's given by Euler's formula, okay, which says that the real part is cosine of theta, the imaginary part is sine of theta. Okay, so that means that if I had changed theta, it'll sort of be creating a circle of radius 1 in the complex plane. So as theta changes as a real value, e to the theta I is just spinning around the circle, from your point of view, this way. Okay? And this clarifies a lot of stuff if you're messing around with complex numbers a lot. But you get a couple nice identities. That means that sort of pi represents half a circle, 2 pi represents one whole circle. Okay? So in particular, e to the pi I is a half circle, gets us to -1. No. To -1. And e to the 2 pi will get you all the way around and back to 1. Okay? We'll need these as facts. Okay? Alright, one last set of definitions. Roots of unity. Okay, so these are numbers where the nth power is equal to 1. Okay, so for any n, the number 1 is the nth root of unity, because 1 to the 10 is equal to 1, 1 to the 100 is equal to 1, of course. -1 is a root of unity whenever n is even, right? Because -1 squared is 1, -1 to the 4th is 1, -1 to the 100 is 1, -1 to 101 is -1. Imaginary I is a 4th root of unity, because I to the 4th is the same as I squared times I squared. I squared is -1. So -1 gets you 1. Okay, so if we're only looking at real values, there's not that many roots of unity, but in the complex plane there are. Okay, in particular, by Euler's identity, if I looked at e to the 2 pi I over n, so that's sort of a small rotation, 1/n of a rotation. If I multiply that by, if I take that to the nth power, that'll repeat itself n times and go all the way around the circle and get me to 1. Okay, so e to the 2 pi I over n is one of these so-called nth roots of unity for any n. Okay, so that represents a small rotation in the complex plane. And it turns out that this generates all of the roots of unity. So if I squared it and then took it to the n, you'll again get 2 rotations around the circle. If I looked at e to the, so all of these are kind of going around the clock, 1/n of a rotation at a time. These will be in fact all of the nth roots of unity. Okay. Alright, so, okay. Those are the definitions. What is this Fourier transform? Okay, so the input. You're taking n complex values. Okay? And we're going to think of that as coefficients of a degree n-1 polynomial. Okay, so you just give me n values, but I'm interpreting it as encoding a polynomial. Okay? And what the Fourier transform does, it just takes this polynomial and the nth Fourier transform. It evaluates the polynomial at all nth roots of unity. Okay? Takes a polynomial with n coefficients, evaluates it at n points, and returns those complex values. Okay, that's all we're trying to do. Okay. There is a conjugate, sorry, I'm missing a sign, f star n of a. It'll be motivated in just a second. But rather than, it's really evaluating the same thing, except instead of kind of going in, say, clockwise order, you're going in counterclockwise order. So you're looking at the nth root to the -1, nth root to the -2, nth root to the -3, which is really just a rearrangement of the first Fourier transform. So if you can compute Fn, you can compute Fn star. All right. So that's just a definition. We're just taking a polynomial and evaluating it at n particular points. Now, it's not at all clear why that's useful. Okay, so let's see. Okay. It's also clear now why we had f star n. All right, so here are 2 facts. All or a fact and an algorithm. One is that Fn and Fn star are roughly inverse to one another. Okay, so what is this saying? I take my coefficients A, which I think of as a polynomial, and Fn of A evaluates it at n roots of unity. Okay? And that gives me n values, complex values. And Fn star is taking those values and reinterpreting them as coefficients of a polynomial and evaluating n roots of unity except in some reverse order. Okay? So I take coefficients, evaluate, get some values, interpret the values as coefficients, evaluate, get some values. That second set of values gives you the original coefficients times n. You can divide by n to get the exact coefficients. Okay? But the point is that Fn star basically will undo Fn. Okay, so that's important that we can invert this. And Fn star is algorithmically very similar to Fn. That's also useful. Okay. Now the algorithmic part, which is really the point, we might skip proving fact 11.4 and focus on the algorithmic aspects. So, again, we're taking a polynomial with n coefficients, and we're evaluating p of x at n different choices of x. So naively, if you just plugged in and multiply, and you added things up, it would take linear time for each evaluation. So you would need n squared to get all n values. Right? Just evaluating a degree n polynomial at n points takes n squared time. But what we're going to show is that because we're only interested in the roots of unity, which is very special and they're closely related, we can do all of them in n log n time. Okay, so we're going from n squared to n log n. Okay, it's still not at all clear why this is useful, so let me give you an application. Multiplying polynomials. Okay. Suppose I had 2 degree n polynomials. Or degree n minus 1, so that's n coefficients. That's one. Here's another. So this one will have b's. Okay. Now, suppose I wanted to compute the product. No. Suppose I wanted to compute the product. R of x is equal to P of x, Q of x. Like I wanted to get the coefficients of R. Okay, so say R of x is equal to C0 plus C1x plus C2x squared plus so forth. I guess the degree could be n minus 2, 2n minus 2. Okay? Let's say I wanted to calculate R. Now that's a natural thing to do. Okay? Now, the old-fashioned way to do this is to take ck and realize that ck, right, that's the coefficient for x at a k. And that's sort of multiplying all those pairs that'll give me degree k. So it'll be the sum from I equals 0 to k of ai b to the k minus I. Right, because x to the I times x to the k minus I will give me x to the k. Right, so I'm, this kind of zipping things up. This is, for some reason, it's called a convolution. Okay. Now, if I did that to generate all the coefficients, I would need n squared time because each of those sums represents a large loop. And I need n coefficients. Okay, so naively multiplying 2 polynomials together would take n squared time. Very similar to integer multiplication. Okay. But now, let's look at this. Okay, so let's look at the roots of unity. So I know that, for example, if I'm, say, even just taking the first one, the value of R at this primitive nth root of unity is equal to P of omega n times Q of omega n. Right? Just because R is the product of P and Q. So I'm just evaluating P, I'm evaluating Q, I'm multiplying it together. That gives me the value of R. Okay? But obviously, if I had the right-hand side, I only need constant time to multiply those things together. So as opposed to doing a loop to generate a coefficient, I only need constant time to generate one of the values of roots of unity. Okay. And I know that if I knew the value of R at all the roots of unity, I would be able to get back the original polynomial. Flood warning, okay. I'll be able to get the original polynomial by doing the kind of un-Fourier transform, the conjugate Fourier transform. Okay? So what would then be an algorithm? Actually, we would probably need the 2nth because R has degree 2n. Okay, so I can start with my two polynomials. Okay? And I'm going to apply that 2nth Fourier transform to each one. Okay, this will take me n log n time. And I'll get all the values at the roots of unity. 2n, p omega 2n squared. The last one is 1. I'll also get q omega 2n, omega 2n squared. Okay? So I can get all these values in n log n time, not n squared time. And now I just multiply them pairwise. Okay? So I can multiply them pairwise, right? And in constant time for each one, I can get the corresponding values for R. Okay, so given the values for P and Q, I can get the values for R just by multiplying them together. Okay. And then I can apply this sort of inverse version, Fn star, to those values, and I get back the coefficients times n. So I'll get C0, C1, C2, C2n minus 1 or something. Right? So I can get back the original polynomial by undoing that Fourier transform using the so-called conjugate Fourier transform. This takes me n log n time. Okay. The coefficients are scaled up by n, so you divide by n, no big deal. Okay. But if I zoom out, right, I've taken two polynomials of degree n, or n minus 1, and I've multiplied them together in n log n times total. How? First take the Fourier transform, that gives me n values. Multiply the values together, that's easy. And then undo that transform to get the polynomial. It feels like cheating. It feels like magic. Okay. Alright, so that's one application of Fourier transforms. Okay, so we have 10 minutes left. So, so what was set up was, at some level, the reason why it was useful for the application was not only because we had the Fourier transform, but because we had an inverse operation. We can undo the Fourier transform using roughly the Fourier transform again. Okay, but that's not algorithmic. That's just some math. Okay, so let me skip that for a moment. If we have time, we can come back. Otherwise, it's in the notes. It's like a page. It's just some algebra. What's really going on is that as the Fourier transform is a linear function, so it can be represented by the matrix. That matrix is Hermitian, which means it's symmetric, except if you also take the complex adjoint, you get back itself. And so it's a unitary, and it doesn't matter. Okay. But I just did the sums and notes. Okay, so we'll take this as a fact, that you can undo the Fourier transform with the conjugate Fourier transform, which again was very similar to Fourier transform. If you can have an algorithm for Fourier, you get an algorithm for the conjugate. Okay, so I'll omit this in the interest of time. We'll focus on the algorithmic aspect. Okay? So you give me input, the coefficients of a polynomial, and I just want to evaluate the polynomial at these n specific values called the nth roots of unity. If I do that, then you can do clever things like multiplying polynomials and stuff like that. Okay? Let me make sure I don't goof this up. Okay. All right, so we're going to need basically one very silly trick to set up the divide and conquer. Okay? And this will explain why we're interested in evaluating the roots of unity compared to other points. Okay. So look at this. All right, omega, the 2nth root of unity. Okay? Which, if you remember the definition, was e to the 2 pi I divided by 2n. Okay? Why? Because then if you take it to the 2nth power, you'll get e to the 2 pi I. That represents one rotation. That's 1. Okay? All right. But if I look now at omega 2n squared I'm just squaring, and I can cancel out a pair of 2's. Okay. E to 2 pi I over n. And this is equal to the nth root of unity. Okay, so there's some kind of doubling trick going on here. Okay, there's a little extra symmetry. Okay, algebraically simple, but still kind of funky. Okay, so from now on, I'm going to assume that n is a power of 2. If your polynomial wasn't a power of 2, just add a bunch of leading zeros, make it a power of 2. It won't change n by more than a factor of 2. Okay, because what we're going to do is we're going to kind of keep dividing n by 2. Okay. You don't really have to. The code I give doesn't assume this, but it'll be easier for our discussion. Okay, so let's look at f sub n of a. Okay? And let's look at the ith coordinate, so to speak, which is to say that's evaluating the ith root of unity. So I'm kind of indexing starting from 0. I usually do starting from 1, but because we usually do a0 for degree 0, it's more convenient this way. Okay? All right, so if I just write this out, this is a0 plus a1 Okay, I'm just writing out the polynomial. Okay, so that's what we're trying to compute for all i's. Okay, but now let me take those terms and group it into sort of the even indices and the odd indices. Okay, a0 plus a2. No, don't stop. Sorry, Siri wanted to participate. Sorry. Omega 2i and a4 omega 4i and so forth. Okay, so this is all the even powers. Nope. this is all the even powers. Right? And I can below have all the odd powers. Cubed. Okay, so I've just taken that first sum, split it into two sums. That's going to be the division of our divide and conquer. Okay. Now, let's just look at the even sum. Okay, so we know that omega n squared is equal to omega n over 2. Again, I'm assuming n is even and everything's a power of 2, so I don't have to write floors and ceilings and stuff like that. Okay. All right, so what I'm going to do then is I'm going to apply that to every one of these terms. Okay, so we get A0 plus A2 times omega n over 2 to the I. Okay. Plus A4 omega n over 2. Oh, I shouldn't have chosen I because, damn it. That's a regular I, not the imaginary I. That's the only value I shouldn't have chosen, but it's too late. I's and J's, okay. Okay, this will be I squared plus A6 omega to the I n over 2 cubed, right? Because 6 gets divided by 2 becomes 3. Okay. A n minus 2 n over 2 minus 1 kind of thing. Okay? All right, so why is this interesting? Let's look at this vector, A even, of just the even coefficients. A0, A2, A4, up to an minus 2. Okay? Then, what we actually have here is the Fourier transform, but now n over 2 instead of n, of just your even coefficients. Okay, because somewhere we did this squaring trick with the roots of unity, and roughly we were able to halve things. Okay. All right, so what that would let us do then is say, oh, so this part, this is recursively like another Fourier transform of just the even coefficients. Okay, by the squaring trick. Again, some of it was very simple, but I understand that every definition at play is brand new, so it feels probably crazy. But all we're doing is kind of squaring and stuff like that. Okay. And down here, okay, if you look down here, I missed one term. Again, today. Down below, you do have odd powers, right? So you can't just divide by 2. Okay? But what you can do is you pull out one term, and then everything left is even. Okay? So this would be equal to, I pull out one of these, and I get A1 plus A3. I'm not sure why. Today is different than other days. It's very risky. Anders, no, okay. Okay. So if I pull out one copy of the nth root of unity, the ith one, then everything inside is even. The powers of omega are even. Okay? So I can write this as, I'll skip the calculations in the interest of time, but again we'll get the Fourier transform of half of n for only the odd coefficients. Okay? Alright, that seems like algebraic a lot, but what have we done? We've taken the Fourier transform for n and turned it into two Fourier transforms of n over 2. Okay? It's exactly like merge sort, it's exactly like closest pair. The algebra may seem odd, but it's believable. Okay? Let's see if I put the code somewhere. Maybe I forgot. Okay, so let me end by presenting the code, and it'll be clear why the running time is fast. Okay, so this is it. Okay? So what's the code doing? I'm pulling out the even coefficients, the odd coefficients. I'm calculating the Fourier for the even coefficients. I'm calculating the Fourier for the odd coefficients. And based on exactly what we just did, I'm multiplying things back in to get the values that we're actually looking for. Just based on exactly those calculations we just did. It should probably be n, not 2 to the n. And then I return them. Okay? So this is why you can evaluate n values in n log n time. It's because for roots of unity, somehow you can do this squaring trick and get some divide and conquer going. That's not true if we're evaluating other arbitrary points. But the roots of unity, because of this whole rotation thing and periodicity, is particularly convenient algebraically. Okay? It all seems crazy, but something useful you can do is multiply two polynomials together much faster than you can do naively. So that should at least be compelling. Okay? And you'll need that for the homework. Okay, that's all. Thank you.